In this video, we're trying to explain the binomial theorem and then look at a few examples of the theorem. This is section 7.4. It would be the last section for us in the college algebra class. So, section 7.4, the binomial theorem. Now, I've written the objective of what we want to do. It's very simple. Here's our objective. We simply want to expand the binomial. The binomial we're expanding is this binomial, x plus y to the n. That's all we want to do. Of course, there will be variations. It's not always just x and y. It could be expressions other than those. But the key is that we have a binomial, meaning two terms, and we are raising it to an integer power. More specifically, we are raising it to a positive integer, of course, including 0. So let's call it a whole number. How's that? We're going to raise the binomial to a whole number power. Now, what I've done here is actually copied from the book. These are the first few expansions of the first one, x plus y to 0. Well, anything to 0 power is 1, so that expansion is simply 1. It has one term. What if we expand x plus y to the first power? Well, x plus y to the first means just x plus y, right? Anything to a first power is itself. So that's the expansion. So far easy. X plus y squared. I'm sure most of you can do that one. We have a special product, special factoring formula, if you will. But view it as a special product. X plus y times x plus y. You can FOIL it, and you can actually get this expression to the right. And look at x plus y cubed. Now, as the exponent gets bigger, by the way, the right side gets more and more complicated. True? So the question is, well, how can we do this if we want to do, for example, x plus y to the 8th power? Now, but remember, this is the objective. That's what we want to do. Now, looking at what's on the right side here, to the right of these equations, and we can kind of draw a parallel to what's called Pascal's triangle. Some of you may have seen the Pascal's triangle, right? Which is named after Blaise Pascal. This idea, by the way, is roughly about 400 years old. However, Pascal wasn't the first one who come up with this binomial expansion. Indeed, Chinese scripts show that Chinese have done this long before Pascal. But in the book, it's called Pascal's triangle. It's named in his honor. Okay? So we're just going to let it slide this time. Now, and one thing that Pascal's triangle does is actually gives us the coefficients on these expressions. Let me explain how this works. So row 0, okay, row 0, that would be, I guess, considered as row 1. And this here, we have row 2, row 3, row 4, row 5, row 6 in that expansion. Okay, now, going beyond row 1, just a trivial one here. Let's take a look at x plus y. Well, when we say x plus y, we are really saying what we can rewrite it as 1x plus 1y. So the coefficients on x and y on the expansion are 1, 1. Okay, that's interesting. Let's look at this for expansion of x plus y squared. So I have 1x squared, 2xy, 1y squared, and there you go. Those are the coefficients. And you can see so on and so forth. So the next row of this work is 1, 3, 3, 1. And there it is in Pascal's triangle. So it's very interesting that we can see this in this nice pyramid of numbers. Now this pattern, how does this pattern work? We can go from one row to the next and to the next this way. So for instance, starting with row 1, if you add 1 plus 1, you get 2. That would be the number in the middle of the next row. One thing we can observe actually here is this, folks. Every row starts with 1 and ends with 1, other than the first row, which has just got one number. So let's just not include that one. And there you go. Every row beyond row 0 has 1 in the beginning and 1 in the end. And then it has numbers in between. The numbers in between are found using Pascal's triangle in this way. So for example, how do we get the numbers in this row? Well, if you do 1 plus 2, you get 3. 2 plus 1, you get 3. And remember, we start and end every row with 1. So that would be the third row of Pascal's triangle. Look at this one, for instance. For this one, you add 1 plus 4. 1 plus 4, you get 5. 4 and 6 makes 10. 6 and 4, 10. 1 and 4 gives you 5. The start and the ending, starting, ending, are always 1. So this is how we can do this. Now, of course, you can see Pascal's triangle has limitations. For instance, imagine if you want to do x plus y to the 50th power. So I'm going to have a whole huge Pascal's triangle that surpasses the page length, right? So this is nice, cool and everything, but we just cannot, it's not practical for higher powers. And the Pascal triangle itself, by the way, has a lot of interesting properties too. You look at this one, for example, you see 1, 2, 3, 4, 5, 6. You look at these numbers. There's a pattern in every row. There's a pattern in almost every column. And there's a pattern in every diagonal of this Pascal's triangle. See that 1, 3, 6, 10 I circled? 1, 3, 6, 10 going in the other direction. And again, each of these form their own sequences. So you can read more about Pascal's triangle and fascinating facts about it. Go to Google and you can find this. Now, remember, our objective is how we're going to do this without Pascal's triangle. So in a moment, I'm going to be doing x plus y to the 5th because we have the answer for it. But before we do that, we need to get past a couple of ideas. The first one is factorials. The factorials, and the exclamation mark means factorial, is simply defined for every positive integer. By definition, 0 factorial is 1 and not 0. And the other factorials, n factorial, is product of n and every number less than n all the way down to 1. Okay, so for example, let's say, for example, I want to do 3 factorial. The fact that it's a factor means I have to multiply. And the pattern of multiplication is always what the number you start with, and then you subtract 1 each time you go to the next factor. You work your way all the way to 1. So 3 factorial is 6. You can actually multiply the factors. What is 5 factorial? Well, 5 is 5, 4, 3, 2, 1, right? The product of those. That's going to be, 120? As you can see, factorials grow very rapidly. Just go from 5 to 6 factorial. You're going to do 6, 5, 4, 3, 2, 1, which you can write if you like as 6 times 5 factorial, because that's what this is. And we just did that one above. That's 6 times 120. 720. See how this factorial function grows? It grows astronomically, very quickly. In fact, a lot of older calculators, I don't know about today calculators, you can try and see if you can test the capacity of your calculators. Try to do 100 factorial. See if your calculator can handle it. The older calculators, like the one I had, could only handle 62 factorial. This was my calculator a long time ago. I'm sure calculators have improved and they can do more than that. For large factorials, by the way, there is a way to approximate them. The approximation is done using Stirling's formula. I just put the proverbial bug in your ears, Stirling's formula. You can again Google this one and see how it works. Stirling's formula for approximating large factorials beyond the capacity of our calculators. Okay, so now that we've talked about factorials, let's talk about the binomial coefficient. And at this point, I just want to call these the NR combination. This formula that you're seeing, it's read as combination of n things chosen R at the time. So I'm giving it a combinatoric definition rather than calling it the binomial coefficients, but that's what they ended up being. So, and in fact, C here stands for combination. See the C there. So the root of this goes back to the field of combinatorics. Now, let's see how this is going to work out. Okay. Suppose I want to, let's say, evaluate something simple. Example. Let's say we want to do 9, choose 3. Oh, the way we read this, by the way, the notation. I can write this as combination 9. 9 things chosen 3 at a time. Or some people call this just N choose R. That's also very common. So what I have written in my example is 9 choose 3. Which may suggest, what is it that we're choosing, right? What do we say choose? What is it exactly we're choosing, right? That's legit. So what we're choosing is this. Suppose I have nine people, and I want to choose, and hence the word choose. Suppose I want to choose 3 people out of 9 people, and do something, and form a, let's say, I don't know, form a committee. Okay. And, or better yet, I'm going to choose 3 people and send them to Disneyland out of 9 people. So the question is, how many ways can I choose subsets of size 3 from 9? That's what this turns out to be. So this combination of C and 3 gives us the number of subsets. Let me do this and then I'll write what I just said. This is totally away from binomial coefficient, but there's commonality there. So let's write this thing out. According to the formula, 9 factorial, the denominator is going to be 3 factorial, 9 minus 3 factorial. Okay, so here's the top, 9 factorial. In the denominator, 3 factorial. Then we do parentheses, 9 minus 3 is 6 factorial. All right. Now, we can do this a number of ways. I can go 9, 8, 7, 6, 5, 4, 3, 2, 1, or stop at 6 and factorial it. 3 factorial is 3, 2, 1, no question there. And 6 factorial, again, is a large number. In fact, we did it here, 720. But because it's 720 on top, 720 on the bottom, we can actually cross those out, couldn't we? Because they're common factors, quote unquote factor. Now, I can simplify the rest. 8 divided by 2 is 4, 9 divided by 3 is 3. So, all said and done. The denominator, everything goes away. In the numerator, I have 3 times 4, 12 times 7, and that's 84. There you go. So, if I want to choose 3 names from 9 names, there are 84 ways to do this. Okay, so I'm giving it again a combinatoric definition, but for us, can I evaluate 9 choose 3, the binomial coefficient? Sure, this is how you do it. So the answer is going to be 84. Okay, let me do another example. So for this next example, this time I'm going to write it as, let's say I want to find a binomial coefficient, 100, choose 98. This one, the numerator is 100 factorial over the denominator, 98 factorial. Here's n, here's r, and I'm going to the formula above. Okay, and there we have that. And n minus r, that would be 100 minus 98, makes the other part 2. If you note, by the way, the numbers in the denominator, 3, 6 adds to 9. 98 and 2 adds to 100. So that's how we can kind of check our work as we go forward. Now let's evaluate this one. 100 factorial is 100 times 99 times 98, 97, 96, 95, all the way down to 321. But notice I'm stopping at 98 factorial. There is absolutely no need to go all the way down to 1 because I see a 98 factorial in the bottom. 2 factorial is 2 times 1. And check this out. My calculator, it couldn't even handle 98 factorial, but I'm able to do this. Now 100 divided by 2 is 50. So this is 50 times 99. Let's see, 50 times 100, that would be 5,000, right? But it's not 100, it's 99. So I'm going to subtract the 50. The answer should be 4,950. Please check this one. Hopefully that's the right answer. Okay. Now, a lot of the calculators are capable of doing this. Okay. It's just look at your calculators. On your calculators, usually you have these keys. You have this key that says C and R. Very common on the calculators. If you have that button on your calculator or variations of it, then you should be able to do this on your calculator. The numbers we work with, by the way, they're not going to be that large, so you can actually do it the longhand like I'm doing on this video. But make sure you just read your calculator's manual or go to YouTube and search for your calculator and do like combinations, permutations. Search for that and you'll get definitely so many hits, and people show you how to do this on your calculators. Okay. All right, so that's what that answer is. Let's see. So I've done that part. Now let's actually do an expansion. Remember, that was the whole idea of what we're doing here. So our next example is this. And I said I'm going to do, well, let me do an example that will help you with your homework. But this we can definitely do. But let me actually do what's already up here because you have the answer. So let's say I want to do x plus y to the 5th. Okay, now from the expansion, we're going to make a number of observations here, by the way. And notice I'm going to do this without the binomial theorem. And once I'm done with this example, I'll show you the binomial theorem. Hopefully then it will make more sense. Because so I just show you the theorem, you're going to say, what the heck is this? It's not going to look that good. So let's see. The observation we're going to make from the expansion of x plus y to the 1st, 2nd, 3rd, 4th, 5th. We can make quite a few observations here. We already made several observations, right? Every expansion starts with 1 and ends with 1, the coefficients, right? Let's see. For x plus y to the 5th, that's my focus. The exponent n is 5. 1, 2, 3, 4, 5, 6. There are 6 terms in the expansion, right? Look at x plus y to the 4th. There are 4 terms, but then there are 1, 2, 3, 4, 5 terms in the expansion. So the number of terms in the expansion, it's going to be 1 more than the number in the exponent on the binomial. Okay? So the expansion of x plus y to the 5th, the first term is going to be x to the 5th. The last term is going to be y to the 5th, each with a coefficient of 1. There will be 6 terms in the expansion. Now, that's another observation I was going to make. Look at the first term, x plus y to the 5th. First term is x to the 5th. Last term is y to the 5th. Look at x plus y cubed. You have x cubed, y cubed. There you go. And by the way, x plus y cubed, common mistake. This is not x cubed plus y cubed. As you can see, that's what x plus y cubed is. So please do not make that mistake because it is incorrect. All right, now let's see what else. the observations we made. So the first term is going to be x to the nth power. The last would be the second term to the nth power. Good. Now look at every term in between. Every term other than first and last is going to have x and y together. xy, 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 like that. True? You have xy, 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 xy. Now, look at the exponent. Forget the 5, the 10, and the 5. I'll show you how to get those without the Pascal's triangle. But look at the terms. Each term has both x and y together. Look at the exponent on x. The exponent on x starts with 5, then it goes down to 4, 3, 2, 1, nothing. Look at the exponent on y. The exponent on y goes the other direction. It goes 1, 2, 3, 4, then 5. Okay. And the other interesting, the last thing we're going to observe, and I'm going to go down and actually do these observations, write them out. If you look at the exponent on each of these terms, this one, this one, this one, and this one. The exponent 4 plus 1 is 5. 3 plus 2, 5. 2 plus 3, 5. 1 plus 4, 5. Which is the n, the power we are raising the binomial to. Got it? Now let's put all of this together. I'm going to go down. We're going to do this strictly using the patterns we see. The coefficients we're going to hold off, but I'm going to put a fraction line here for the coefficients. Why do we need a fraction line? Because it ends up that the coefficients are given by the binomial coefficient. Okay, so remember, other than first and last term, we're going to have x, y together, plus another fraction, x, y together, plus another fraction, x, y together, plus. So how many of these fractions do I need? Well, there are 6 terms in the expansion. We have the first, we have the last. 6 minus 2, take the first and the last. I need 4 terms with fractions. This would be the last term with a fraction, and the last term is y to the 5th. So far, so good. Now, look at the exponents. The exponent on x starts with 5. Next one would be 4, 3, 2, 1, and the last one, x to 0, which we don't write, down to nothing. And let's take a look at the exponent on y. Starts with 1, then it goes to 2, then it goes to 3, then 4, and of course the 5 here, right? Don't need that one. So we pretty much have the skeleton of the binomial expansion. All we need are the numbers that are in Pascal's triangle without using Pascal's triangle. So here's how that works. For the numbers that go in the fraction, the numerator of every fraction is going to be n factorial. There, isn't that cool? And for the denominator, I copy and paste these exponents into the denominator, but be sure to factorial them. So 4, 1 becomes 4 factorial, 1 factorial, 3, 2. That's 3 factorial, 2 factorial. 2, 3. That's 2 factorial, 3 factorial. Isn't that cool? 1 factorial, 4 factorial. And this way, I can actually remember the patterns. I don't have to memorize the binomial theorem. That's the key. And there you have it. That is the binomial expansion. So let's complete this now. This will equal x to the 5th. So the question is, what is 5 factorial, 4 factorial, 1 factorial? That's 5 times 4, 3, 2, 1. The bottom is 4, 3, 2, 1. 1 factorial is 1. The answer is 5. Plus 5 x to the fourth y. Next fraction is this one. 5 factorial, 3 factorial, 2 factorial. You want to write it out. The numerator, 5, 4, 3, 2, 1. The bottom, 3, 2, 1 times 2, 1. Right? 3 factorial, 2 factorial. 1, 2, 3, 1, 2, 3. Top, bottom cancels. On top, I have 20. The bottom, 2. 20 by 2 is 10. So here's your next number, 10. And we're going to go x cubed y squared. Now let's go back, look at the answer so far. Notice we have 1, 5, 10. Look at this one. You got your 1, 5, 10. 1, 5, 10 in Pascal's triangle. Right? Now here's the other cool thing. If you look at the expansion, this would be, I got 6 terms, right? This is the center of expansion, isn't it? Look at the numbers on either side. 10, 10, 5, 5, 1, 1. Isn't that cool again? You can look at it in Pascal's triangle. 10, 10, 5, 5, 1, 1. Symmetric. Look at the row above, row 4. Here's the center number. On either side, adjacent sides, you got 4, 4, 1, 1. Look at this one, 3, 3. Look at this one, 1, 1. So there's another cool thing about this Pascal's triangle is its symmetry. Okay, what does that mean for us? Well, if you look at 5 factorial, 3 factorial, 2 factorial, next to that is 5 factorial divided by 2 factorial, 3 factorial. These denominators are equal. So you can use the symmetry so you don't have to reevaluate this. I'm just going to go, the next number is going to be 10. The exponent on x is going to be dropped by 1. It's going to be picked up by 1 using y. And plus, so I've done first, second, third, fourth term. 1, 2, 3, 4. 2 more terms. This one. It's going to be symmetry. It's going to be 5 just like the one above it is. Right? The exponent on x, it's 2 here. Now next one is 1. The exponent on y is 3. For the next term, it would be 4. And finally, the last one is y to the 5th. Now, look at the exponents. 5, 5, 5, 5, 5, 5. Every exponent is going to be 5. True? Which is the exponent on the binomial x plus y to the 5th. Okay. And there you go. You're looking at the binomial expansion. We did it. So this is the easiest way to do the expansion without even calling the binomial theorem. But now that we've done this, let me actually show you the binomial theorem. Okay, and here it is. This is the infamous binomial theorem. See that? I don't know about you, but I prefer the way we did it here. The theorem works, of course. It's worked for hundreds of years. It's still going to work. And here's the theorem, by the way. You're welcome to read it for your own. It starts with x to the n, ends with y to the n. And then in between, see that? You subtract an exponent from x. Each term, you subtract 1 and so forth. And y actually gains 1 each time. So they're basically copying the patterns that we just saw, except with general descriptions. The coefficients in front, there you go. These are the binomial coefficients that you're looking at. Feel free to work with these the way they look, or again, if you're like me, I would suggest doing the pattern. Okay, so let's do one more. Let's do another example here. I'm going to use the pattern. I'm going to ignore totally this thing. Oh, and by the way, you can write that in summation notation for those that are interested. And typically, by the way, these binomial series, you're going to work with these if you pursue this endeavor. You're going to see them in the second semester calculus. There is a chapter in second semester calculus called Sequences and Series. And a very elaborate chapter. We usually spend about a month in that chapter. So there you go. This is the form that we work with in higher math. So let's take a look at an example. In this example, suppose I want to do this. I'm just going to do expansion of p plus 2q to the fourth power. Okay, and I'm going to do it exactly the way we did the one above. I'm going to use patterns. Now remember, the exponent, this is n. N is 4. So how many terms will there be in the expansion? It's going to be 1 more than n, right? So there's going to be 4 plus 1, 5 terms in expansion. So I'm preparing myself for 1, 2, 3, 4, 5 terms here. Now, remember the first and the last terms, what they were? The first term, it was x to the n, where instead of x, we have p. So I'm going to write it now. It's going to be p to the fourth. That's the first one. Remember what the last one was. Side by side plus fraction, side by side, thinking side by side on the variables. Plus, oh, remember 5 terms. First term, p to the fourth. Last term, the fifth term. First, second, third, fourth. I can do one more of these and then put the last term. The last term, remember, was y to the power. Instead of y, we have 2q. So it's going to be 2q to the fourth. First one to the fourth, last one to the fourth. Now, in between, we're going to have 3 terms. Side by side. So it's going to be p times, I'm going to put 2q in parentheses. P times 2q in parentheses, because it's 2 times q. If it was just q, I wouldn't do that. P 2q. Right? Aside from the first, aside from the last. In between, every term will have both first and second term in the binomial. This is the first, this is the second. All right. Now, what about the exponents? The exponents on p. Remember, we started with 4. What would it be on the next one? 3, right? 1 less. The one after that, what will be the exponent on p? 2. The one after that, 1. Each time you decrease by 1, down to nothing. And what about the exponent on 2q? Starts with 1, then you increase by 1, increase by 1. Look at the exponents. 3 and 1, 4. 4, 4, 4, 4. Isn't that what n is? N is 4, right? So that's just a quick check for me to make sure I did this right. And next step, what about the numerator of each fraction? The first fraction, n factorial. Second one, n factorial. And the third one. How about the denominators? Remember how I got the denominators? Copy, paste, copy, paste, copy, paste. Make sure you factorial them. So this would be 3 factorial, 1 factorial. Next one would be 2 factorial, 2 factorial. Next one, 1 factorial, 3 factorial. And hopefully this is all good. And there's your expansion, folks. We just did this beast. And I didn't even honestly look at it on, I don't even know how to read this thing, right? But we can do it. I'm just kidding. I mean, I know how to read, but you get the idea, right? We don't really need to go through details. Okay, what is this? What is this? All right, let's simplify this thing. P to the fourth plus. The factorials, 4 factorial over 3 factorial. 1 factorial is 1. 1, 2, 3, 1, 2, 3. So this is just 4. p cubed and 2q to the first power. Isn't that just 2q itself? Let's do 4 factorial over, I'm doing this one, over 2 factorial, 2 factorial. 1, 2, 1, 2. 4 by 2 is 2. 2 times 3 is 6. So this is going to be 6 p squared. And we're doing 2q squared, right? Don't forget, you're squaring the whole 2q, not just q. 2 squared is 4. Q squared is q squared. So that's just 4q squared. Good? So far, so good. And then I'm going to use symmetry now, folks. Look at this. 4 over 3 factorial, 1 factorial will be exactly the same as 4 over 1 factorial, 3 factorial. And that we found it to be 4. So this is going to be plus 4 p 2q cubed. 2q cubed. That's going to be 8q cubed. Sounds funny. 8q cubed. There it is. And what about the last one? The last one is 2q fourth. 2q to the fourth means 2 to the fourth, q to the fourth, doesn't it? 2 to the fourth, 2 by 2 by 2 by 2. 16q fourth. That's going to be plus 16q fourth. And there you have it, ladies and gentlemen. That's the expansion. Now, we can still simplify this, right? Remember, we always simplify to the lowest form. They're not going to have to tell us. 4 times 2, 8. P cubed, Q. 6 by 4. 24. P squared, Q squared. Plus 4 by 8. 32. P Q cubed. Sound like the sound of that. Q cubed. And finally, the last one is 16q fourth. And there you go. Take that to the bank. All right. And there is the full expansion. Now, if you note, by the way, one thing to explain in the full expansion, there is no symmetry in these numbers. Oops, I don't know what happened. There's no symmetry in these numbers, right? There was symmetry in the binomial coefficients, these, right? But there's no symmetry in the final answer. And the reason is because of that 2q, right? It kind of throws it off symmetry. And that's why. There's nothing we did wrong. And that's the full expansion again, everyone. So we're good with this one. Now, one last idea. And for this last idea is this. Let's look at the patterns again, going back to this one. Let's say I'm going to look at the third term in the expansion of x plus y to the fifth. First, second, third. Okay, so looking at the third term in the expansion, the exponent on y is 2. The term is the third term. This one, for example, is the fourth, and so on. Now look at the exponent on y's. For third, it is 2. For fourth, it is 3, isn't it? Okay, check this out. That's going to be inspiration for my next example. Let's say I want to expand 2x plus 3y to the 11th power. Now don't worry, I'm not going to expand this. We don't want to have 12 terms in the expansion. Sometimes we just want to know what is the value of a single expression in the expansion. So for example, let's say I want to find the 8th term in expansion. The idea is this. I want to find a single term. You see that? I don't want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms. Who cares? That's just too many, right? what about just a single term? So for the single term, I'm going to use again the pattern that we saw that I mentioned about in here. Remember I said first, second, third. For third term, the exponent on y is 2. On the fourth term, the exponent is 3. So the exponent on the second variable, namely y, in x plus y to the n. This is the second variable. The exponent on that is going to be 1 less than the term number. So, and remember, aside from the first and the last, remember, the first is going to be 2x to the 11th, last 3y to the 11th. That we know. Every term in between, it's going to be 2x and 3y side by side, isn't it? Just like it was up here, side by side, side by side, side by side. And I messed this one up, sorry. There you go. Okay, so I'm going to do that. In the 8th term, I'm definitely going to have 2x. I'm definitely going to have 3y. Those will be side by side because they're not, my 8th term is not the first term and it is not the last term. Now, what will the exponent you think on the second term be? For the 8th term, remember before? The power on the second variable is going to be 1 less than the term number. So this is going to be 7. And remember what the exponents should add to? They should add to n. So that means the exponent on 2x must be what? What adds to 11? 7 and 4 add to 11, don't they? And there you go. Isn't that cool? See how we're doing this? In front, there's going to be a fraction. Every term other than first, last, there's going to be a fraction in ahead of those products. These products. Now there's my fraction. What do you think the numerator of the fraction is going to be? Remember for my example, n was 4. Look at the numerators. They're all 4 factorial, right? In other words, n factorial. N is 11. Aha. 11 factorial. And the denominator, remember how I got my denominators? Copy and paste. Make sure you factorial it. And there you have it. This would be the 8th term in the expansion. That's what it looks like. Now, let's tidy up. Because remember, we always have to simplify this. True? So, for simplification step now, I'm going to do the factorial and then work the 2 to the 4th and 3 to the 7th. All right. First, the factorial. 11 factorial is 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? Notice I just called it out. I didn't write it. The reason, because I see a 7 factorial at the bottom. Those, whatever they are, they cancel. Let's see. 4 times 2 in the bottom cancels with the 8. 9 divided by 3 is 3. So in the numerator, all I have is 11 times 30. And that's 330. You see, isn't that cool? How you can actually easily do these without a calculator. But you're welcome, of course. I'm sure you use calculators. But there is a way to do without. So the fraction is 330. Now let's simplify 2x to the 4th. 2x to the 4th, that's 2 to the 4th, x to the 4th. 3y 7th, that's 3 to the 7th, y to the 7th. Now I have to do this product. Okay, so for this product now, 2 to the 4th, that's going to be 2 by 2 by 2, right? That's going to be what, 16 times 16. And what about 3 to the 7th? All right, 3 to the 7th. I'm going to do that on my calculator. 3 to the power of 7 is 2,187. X to the 4th, y to the 7th. And in that cool 8th term, here's the exponent on y. And let me multiply the numbers. 2187 times 16 times 330. Wow, big number. 11,547,360. X to the 4th, y to the 7th. And there you go. You have this one. See how that works? And this would be the value of a single term. You can do this for any expansion. And let me show you the formula. And there you go. Notice, remember how I arrived at it? It was very easy. This was my observation. Everything else, I got it from the pattern. But there you go. If you like formulas, there's more formulas for you. This will give you the kth term of a binomial expansion of x plus y to the n. And there you go. And I can actually do this just so you see how it works. So in my example, I just did. We're doing example. I'm going to do it using this formula. See if you get the same answer. 2x plus 3y to the 11th. I want to find the 8th term. So in this work, k is 8, right? Kth term. Okay. The specifics, n is 11. The exponent on the binomial is what n is, because I need it in here. The formula says you do the combination of 11, choose k minus 1, that's 7, times x to the n minus k minus 1, and y to k minus 1. Remember, I said if it's 8, you always subtract 1 for y. There you go. That's right there. Oops, sorry. Let me put k is 8. Just put in all numbers for these letters that you see up here. Okay. And let's see. So how are we going to simplify this? All right. Let's do it. 11, 7, that means 11 factorial over 7 factorial. 11 minus 7 is 4 factorial. X2, 11 minus 7, right? And then it's going to be y to the 7th. Okay. Now 11, x to 11 minus 7, that's going to be x to the 4th, y to the 7th. Oh, let me see. Oh, something I overlooked. So sorry. I'm doing 2x and 3y, right? No, you're saying, what is he doing? There you go. I'll make it work here. Okay. So it's going to be 2 to the 4th times x to the 4th. 3 to the 7th times y to the 7th. And in front, I have 11 factorial, 7 factorial, 4 factorial. And isn't that what I had here? Exactly what I had above. That turned out to be 330. So again, I'm just going to leave it at this point there. Because all of these numbers and factors, you see them up here. I have them. I have 330, 2 to the 4th is 16, but there you go, I have that. 2 to the 4th, 3 to the 7th times 330. That's right in here. So again, I just want to show you how that formula worked, but you can do the formula actually without doing the details of what this formula says. Okay, and there you have it. Now, let me do just one example here real quick, kind of like what you may expect on your homework and on your exam. So let's say I want to find the one term, 17th term in the expansion of a squared plus b to the 22nd power. All right, so how are we going to do this? Remember, for the 17th term, other than first and last, you're going to have both a squared and b side by side, right? The exponent on the second term b is going to be 1 less than the term, so it's going to be 16. The sum of the terms is 22, so that means the exponent on a squared is going to be 6. And then you got your fraction, the numerator 22 factorial, the denominator copy and paste, and there you go. And of course, for these, again, we have to simplify them, right? So it's 22, 21, 20. And I will look on your calculator and make sure you have the button I mentioned, the NCR button, 654321, that's 6 factorial times 16 factorial. Okay, 18. That's 6 by 3, 18 is gone. Let's see, 4 times 5 here is 20. That 20 is gone. 2 times 1, well, 2 and 22 is 11. So I can reduce this to simply 11 times 21 times 19 times 17. That I can do on my calculator again. Okay, so let me do that. On my calculator, I'm doing 11 times 21 times 19 times 17. And the number I got is 74,613. So this is 74,613 times a squared to the 6th. That's a to, you multiply 2 by 6, the power rule. A to the m to the n. The power rule is a to the mn. So I multiply 2 by 6, and then we have b to the 16th power. And there you go, folks. That is your answer. That's going to be the 17th term in this expansion of that binomial. Okay, so, and there you have it. Sorry for the little long video here, but I think it was warranted because there was a lot of material here that we went through. And that's it, folks. So we are done with this section 7.4, and that will conclude the section for us, the binomial theorem. And again, as always, thank you for watching the video, and hope you find it useful. Thank you and take care.